Hey guys, welcome to a new video on chemistry, on the chemistry series. Today I'm going to be talking about electrochemistry, and I'm going to divide this series into three parts. I'm going to talk about oxidation reduction reactions in the first part, then galvanic cells, and standard reduction potentials, understanding the line notation. Then the third part will be cell potential, electrical work, free energy, and in fact, I might go ahead and make a fourth part about batteries and electroplating. Electroplating might, in fact, come into the third part or the fourth part. It's interchangeable. The batteries is extra information, understanding what batteries are what. So yeah. So what is electrochemistry? And in fact, think about all the electronic devices you have today that require a battery. Anything that requires a battery needs electrochemistry. And I have a definition here which I find truly magnificent because it outlines the basis of electrochemistry, and that's oxidation reduction. So here it is. Electrochemistry is a study of the relationship between electron flow and redox reactions. That's where I'm going to stop. Another definition is that electrochemistry is a study of the interchange of chemical and electrical energy. And the interchange of electrical and chemical energy, that is the same thing as the first definition, electron flow. Electron flow is basically flow of electricity. Your redox reactions is the interchange of chemical energy, and that has to be the best definition that I found till today. You can find more definitions on the web. There are more videos describing what electrochemistry is, and yeah, you can research on that. So first I'm going to start off with oxidation reduction reactions, and they occur in aqueous solutions often, but they're most often complicated in aqueous solutions. So we have this half reaction method, and I'm going to go ahead and show you a half reaction method just for balancing the redox reaction in a aqueous solution. So redox reactions, reduction, oxidation. Now what is reduction? Reduction is the gain of electrons. This I'm going to write electrons so I can abbreviate it. And oxidation, I think I spelled oxidation. No, I spelled oxidation correct. Oxidation is the loss of electrons. A simple way to remember this is oil rig, O-I-L-R-I-G. Oxidation is loss, reduction is gain. That is basically a definition of oxidation reduction. Now how to go about in solving a problem is a little bit more complicated. So let's say I have cerium 4, that's cerium 4 Ce 4 plus here, aqueous plus, and then I have a tin 2 ion, so that tin is Sn, 2 implies 2 plus, aqueous, and then in fact it goes to cerium 3. I didn't say if it was aqueous or reduced. That is for you to find out by using the definition I just gave. Did anybody figure it out yet? Well, if not, here, I'm going to go ahead and say it. I need two half reactions, and I'm literally going to take these ceriums out. So I'm going to have cerium 4 plus, somehow is cerium 3 plus, and this substance involved here is being reduced. And how do I know that? Because this is now less positive than it was before. That means it gained electrons. That means it was a reduction reaction. So I'm going to call this a reduction half reaction. And this other reaction, which you're writing down, 10 2 to 10 4 plus, is becoming more positive. It is losing electrons. That means this is an oxidation half reaction. And the procedure for this is to balance these half reactions and then add them up, and you have our overall balanced reaction. But you should know that if you're looking at this video right now. And we're going to go on and balance half reactions in acidic medium and a basic medium. Medium is a solution, for those who don't know what a medium is. So this is a really common example. I have a permanganate ion and an iron 2 ion in an acidic solution. So I'm going to go ahead, MnO4 minus aqueous. Sounds like a song. And it then is iron 3. Wait, what happened to the oxygen? And that's where the half reactions come in place. So let's write down this first half reaction. I have a permanganate ion and all I know at this point is the manganese here has a +2 charge, and the overall ion here has a -1 charge, but I need to know if the manganese has been oxidized or reduced. So I'm going to find out the charge of manganese, and to do that, I know the overall charge here is -1. This negative here implies -1, so I'm going to write down this equation. -1 equals this oxygen, so I'm going to add these, right? So the oxygen has a -2 charge, but there are 4 of them, so that's -8. Oxygen can also have a neutral charge if it's a diatomic gas, but since here it's not, it has a -2 charge, there are 4 of them, that's -8. I want to find out the charge of oxidation number of manganese, so I'm going to write plus X. That means X equals +7, so that means +7 is the oxidation number of manganese. So somehow it gained electrons, right? It became more negative. And this is showing that manganese is reduced. This is a reduction half reaction. Now the other half reaction I'm going to go ahead and write is the one with the iron 2 to the iron 3. And iron 2 to iron 3, it became more positive. It lost electrons. That is what happened. It did not gain electrons, unlike its counterpart, manganese. So therefore, we're going to call this oxidation half reaction. And so we're going to balance these half reactions. Do I have a manganese? Do I have one manganese on each side? Here? Yes, I do. But on this side, I have 4 oxygens. So how am I going to add 4? How am I going to add 4 oxygens here? And no, I'm not going to go ahead and add oxygen gas, but in fact I'm going to go ahead and add water. So I'm going to add 4 waters because H2O, that's 1 oxygen. 4 H2O is 4 oxygens. So I add 4 H2O. That has 4 oxygens. But now I have another problem. I have 8 hydrogens on this side, so I need 8 hydrogens on this side. So I'm going to go ahead and add 8 hydrogen ions. That means protons to you. So I added 8 protons to the left side. Now all these elements have been balanced, but we have to balance the charges. I'm going to go ahead and find the total charge of each side. So this is 8 plus, that's minus, so that's the total charge is a plus 7 on this side. And here, I know water has a plus 0 charge, and the manganese on here has a plus 2, so the overall charge is plus 2. Plus 2 plus 7. So this overall reaction got slightly negative and significantly negative. But to show that to balance this side out with the plus 2, I have to add 5 electrons. So I'm going to go ahead and add 5 electrons. Now this side has the same electron charge, plus 2 on this side and plus 2 on this side. So we have balanced this half reaction. And so now both elements and electrons have been charged. And that's how we know electron charges have been balanced, sorry. And that's how we know if we balance the half reaction, one half reaction at least. Always balance elements first and then balance the charges. And so this represents a balanced reduction half reaction. And then the fact that 5 electrons appear in the reactant side of the equation makes sense since 5 electrons are required, to reduce the MnO4 minus. And so now we're going to move on to the next half reaction, the iron. This is the oxidation reaction. And we know that the elements have been balanced. Now we have to simply balance the electrons. I have a plus 2 and a plus 3 here. Plus 2, plus 3. I have lost an electron, lost in the product. So I'm going to add an electron here. And now this is plus 2. Therefore, I have a balanced half reaction. And now I have to equalize. If you remember from the redox reactions and aqueous solutions, when you have that half reaction, you have to add both of them up and cancel the electrons out. And yeah, so you have to balance. You have to make sure you have the correct number of electrons on each side. So I have to go ahead and equalize electron transfer in the two half reactions. And I'm going to go ahead and multiply this half reaction by 5. Because I can have 5 electrons here in the product side when I go ahead and add the overall reaction, when I make the overall reaction, and I can have the electrons cancel out. So now this reaction is 5 iron 2 yields 5 iron 3 and 5 electrons. And now to add the half reactions, so let's go ahead and add them. Just like a math problem. So 5 electrons, 8 protons, 1 permanganate, sorry. Remember to put your aqueous here. 5 iron 2s yields 5 iron 3s plus 1 manganese 2 4 water, sorry, and 5 electrons. And now I'm going to cancel out the electrons because they have to. And there we have the final final oxidation reaction. The equation is now balanced. And there's another acidic problem I'd like to go through, but before I do that, I'm going to go ahead and work into the basic medium problems. Basic medium example. I'm going to talk only about one basic medium example because it's very similar to the water one, the acidic medium one, but it requires hydroxide rather than just water. So let's say silver is sometimes found in nature as large nuggets, and more often is mixed with other metals and their ores. An aqueous solution containing cyanide ion is often used to extract the silver using the following reaction that occurs in the basic solution. So I have Ag, which is silver, and it's a solid form, guys. Cyanide ion, which is aqueous. And I have oxygen gas. And I have basic, right base, and that goes into silver 2 cyanide. Oh, it's our negative ion right here. It's negative. And you have to balance this equation using the half reaction method. So let's go ahead and balance this equation as if hydrogen ions are present. And I'm going to disregard the oxygen for right now because I'm just going to disregard it for right now. So I have a cyanide plus a silver. This is 1/2 reaction, guys. And I'm going to have to balance the elements first, remember? So I have 2 cyanides here, and so I'm going to need 2 cyanides here. My silvers are balanced. I have to balance the charges. I have a -2 charge, a +0 charge, and a -1 charge. So I went from -2 to -1. I lost an electron. So I'm going to put an electron here. And that is 1/2 reaction. And I'm going to go to the next half reaction. O2, your gas. But there's nothing on this side. There's nothing. So I have to balance it. So I have to add water. So I have 2 waters, liquid. And then I have to balance the hydrogens that I just magically created in the water. So 4 hydrogens, 4 hydrogen ions, 4 protons. To balance the charges, so I know oxygen, has a +0 since it's a diatomic in this example, and there's a +4 charge here. There's a 0 charge here, so I gained 4 electrons, right? So I have to add 4 electrons to the reactant side, and I have 1 electron here, 4 electrons here, and when I'm going to mash these 2 half reactions up, I'm going to have to cancel out the electrons. For that reason, I'm going to go ahead and multiply this reaction by 4. So I have in that case, this is 8, this is 4, this is 4, and this is 4. And I'm going to go ahead and add the reactions up and cancel identical species. So we're going to go ahead and do it right here. 4 electrons are canceled out. So that means I have 8 Cn minus, the 4 silver solids plus the oxygen gas plus the 4 protons, which give us, I'm just going to go ahead and write this on the bottom line because I don't have space here. So that gives us 4 AgCN2 minus plus the 2 waters. And there you go. That's your balanced half reaction. That's the first step, and now you have a second step. So if you thought this was multiple steps, well, I'm sorry, but there are more steps. So we're gonna go ahead, because this is a basic solution. We have to add hydroxide ions to balance the. We have to eliminate the hydrogen ions present, because this is not an acidic solution, and we're gonna go ahead and add hydroxide ions to both sides of the balance equation to eliminate the protons. We need to add 4 hydroxides in this case to each side. So I'm going to go add OH minus 4 of these, and then 4 of these, right? And then we have to eliminate as many as O2 molecules as possible. And we have to sort of change this reaction now, because since I added the 4 hydroxides here, now I have a 4 water molecules. So this has changed. See, this gets really complex, guys. Now I have 4 water molecules, and I have to balance the water molecules. I have to go ahead and balance that out. So I have 4 waters here, 2 waters here, so I completely lose waters on this side, and I only have 2 waters now here. And you can go ahead and check. You can go ahead and check me and see if the elements and the charges are balanced. So let's say that's the 8 Cn minus is -8. That's a 0. That's a 0, and that's a 0. So the reactance is -8. I have 4 -4 from the AgCN2 minus, and -4 from the 4 hydroxide. So that's -8 on this side, -8 on this side. Electrons are balanced. Go ahead and check the elements. 8 CNs. That's 8 CNs. 4 silver. 4 silvers here. 2 water. That's 2 oxygens plus the 2 oxygens. So that's 4 oxygens. 4 oxygens. 4 hydroxide and 4 hydroxide. And there you go. You have balance your basic medium oxidation reduction reaction, and that's the series. That's the part 1 series. In the next series, we're going to go ahead and talk about galvanic cells and standard reduction potentials. How to use the standard reduction potentials table for the half reactions. Talk about anodes, cathodes. So stay tuned for the videos. If you got lost in the past couple minutes, go ahead, send us an email. I'll be happy to clarify the basic half reactions and the acidic half reactions in another example. I'll go ahead and upload another video with more problems on acidic medium and basic medium half reactions in a day or two. So please like and share this video below. Thanks for watching.